Okay, let's take a look at cross-example problem, Unit A2, page 5. Calculate the speed of sound in meter per second for A, gasoline, B, mercury, and C, water. Let's take a look. Okay, speed of sound we covered. If it's gas, of course you know it's a square root of T, and then this K. This is called specific heat ratio. Now in fluid mechanics, we really don't cover what this thing is. You are going to run it from thermodynamics and L1. But you know that for standard air, this is 1.4. Okay? Now, I guess the important thing about this problem is, I guess you need to take a look at it again. You are looking for gasoline, mercury, seawater, speed of sound. Those are not gas, it's a liquid. Now, this is something we didn't cover, but if in case of liquid, speed of sound is given by this equation. EB over rho. EB, this is of course bulk modulus of elasticity. This is a material property for each different type of liquid. Rho is density. So speed of sound really is a measurement of compressibility. Speed of sound tends to be really high if you're talking about liquid, which is liquid is very tough to compress. So it doesn't change the density as easily. Gas is compressible. So speed of sound tends to be lower value compared against those liquids. So this problem demonstrates you how fast it is. If you're looking at the three different types of liquid, what is the speed of sound? So let's take a look at three different types of liquid. A, gasoline. Assuming that the gasoline is a liquid, it's not the gas. Okay. Speed of sound is, like I said, EB over rho. So if you take a look at property table, table 1.6, which is again handout, you can determine bulk modulus of elasticity of gasoline, which is 1.3 times 10 to 9 Newton per meter squared divided by density of gasoline for a given room temperature is 680 kilogram per cubic meters. If you punch those numbers in, you get the meter per second value, which is 1,382.67 meter per second. Okay. B is mercury. Mercury is obviously very heavy liquid. Once again, if you look at the property of mercury, bulk modulus is 2.85 times 10 to the 10th Newton per meter squared divided by density of mercury is also high. 1.36 times 10 to 4 kilogram per meter cube, which is 1,447.61 meter per second. Seawater. you repeat the same process, looking up bulk modulus 2.34 times 10 to 9 Newton per meter squared divided by 1.03 times 10 to the 3 kilogram cubic meters. This is going to be 1,507.26 meter per second. Now, what I want to do here is I want to convert meter per second into miles per hour to see the feeding. In terms of miles per hour, this is 3,092.94 miles per hour. This is 3,238.21 miles per hour. This is 3,371.64 miles per hour. So those are the speed of sound within liquid. Obviously, those are very high values. So one hypothetical question that we oftentimes get from mainly, when we go outreach to like small kids, elementary school kids, they may ask you questions saying, can we make a supersonic submarine? Well, supersonic really means that you need to move faster than the speed of sound, which is this value. So you need to tell them the magnitude of supersonic under the standard condition of seawater is, okay, you are asking about the submarine that can actually move 3,300 miles per hour. If so, yeah, we can have a supersonic submarine. That's what you're talking, okay? Now, one of the reasons why speed of sound is so high is because liquid is very difficult to compress. Bulk modulus is really high value. Liquid is actually can be considered as incompressible fluid. Incompressible fluid. Now, come to think about, if it's indeed incompressible, speed of sound is actually infinity. But in this case, obviously not infinity, but it's very, very close to incompressible. Okay? And also another thing about speed of sound for typical standard air. Let's think about sea level. 760 miles per hour. Okay? So obviously we can have supersonic vehicle, which is relatively low value, okay, compared against those. Alright, that's it.